Okay guys, I know that my videos are boring, and I think I know the reason why, but I'm still going to need your help for me to tweak it and make them better, so I'll be talking to you about this next class. But I think part of the reason is that whenever I lecture to you in class, I am on, okay? I have the tendency to make jokes, tendency to respond to the fact that I can see your faces are completely bored, and here I have no faces for me to gauge what I'm doing as being exciting or not, okay? And I'm able to change it up very quickly in class and do something fun or stupid to give your brains a break, all right? So here, you're responsible for your own brain breaks, and I am delivering the pure boredom, unadulterated boredom, okay? So deal with it, and also I'll try to make it more entertaining. I'll try to pretend like you're here, and I'll start using my smartassness and whatnot to entertain you a bit more, because you deserve to be entertained while educated. Yeah, and entertained with physics, so I'll try to make it interesting that way, all right? So, not much of that's going to happen here, unfortunately. I'll just try to keep my weird, sarcastic, dry sense of humor intact, though, during the time, so every once in a while maybe I'll make a joke and maybe it will spark some sort of enjoyment. Quickly, solutions to numbers 4 and 6, page 243, just wanted to go over these. Number 4, all right, talks about two speakers, and we have an observer walking in a straight line between these speakers. It starts at point M, okay? So there's some important information to write down here. The first is that both these loudspeakers are connected to the same audio oscillator. What that tells us is that both of these sources are coherent, okay? Now, coherence is a very, very important thing when we deal with these interference problems. What it tells us is that both sources have the same frequency and are in phase. If we don't have both of those properties for both of our sources, the interference pattern changes and it's not as easily analyzed, okay? We want to start out with a simple model, and as always in physics, we're building up, okay? We're trying to build these things into more complex models. So the simple model is to have coherent sources. We start out at point M, which is halfway between the speakers, all right? And at point M, we hear a loud sound. That tells us we have constructive interference, okay? Again, constructive interference, both components of the waves adding up to something greater than either of their individual components, right? The resultant component is larger than each of the individual ones. Point P, he walks to, and at that point, it's the first point, he hears no sound. Destructive interference, okay? So we know that the path difference between both of these should be a successive, all right, path difference 1/2 lambda. All right, so I have an image here. These are my crappy speakers. I apologize. This is what you get for a physics teacher is a shitty artist. So, point M, all right, he starts out at, walks towards point P. We see that we're told that the difference in space between M and P is 2 meters, okay? We know this is n equals 0. Why? Well, the path difference right here between M1 and M2 is equal to 0, and that's the first one, okay? First place where we have constructive interference between them, that where n equals 0, okay, where delta L therefore equals 0. So the next place that we have destructive interference, n is still going to be equal to 0, therefore delta L is going to be 1/2 lambda based on our condition that anywhere you have destructive interference is equal to n plus 1/2 lambda, okay? That's got to be the path difference. So we see that P1 minus P2 has to be equal to 1/2 lambda. Well, if we look at P1, okay, I'm calling 1, by the way, the speaker on the left, and 2, the speaker on the right. I'll make that more of a 1. The idea here, okay, is that we've gone 2 meters over to P, but the wave from speaker 1 has to travel 2 extra meters. The wave from speaker 2 has to travel 2 fewer meters. Therefore, in total, both waves have a difference in their paths of 4 meters. Okay, so delta L is equal to 4 meters. We know that the path difference, all right, must be 1/2 lambda in that distance traveled to get there, all right? So 1/2 lambda is equal to 4 meters, therefore lambda must be 8 meters, okay, for us to have constructive interference in the middle and then destructive interference 2 meters to the side. All right, this gets at, in auditoriums, people design things for acoustics, okay? You hear about dead spots, all right? And places where sound cancels out. It may be a fun experiment to try this in our auditorium one day if we get a couple of speakers and a couple of pure tones and walk around the auditorium, and I bet we can find places where the sound will cancel out. Maybe that'll be something we do before Christmas or something like that, a fun little experiment day. So number 6, okay, we're driving between 2 radio towers, both emitting the same frequency of radio waves. That frequency is 90 megahertz. Remember your metric prefix is 10 to the 6th there, okay? Speed of light, we're dealing with light, electromagnetic waves, all right? They all travel at the same speed, so we know the wave speed. We can get the wavelength of a wave, 3.3 meters. All right, good, we got some information here. So, there's a few things to think about here, okay? What's the path difference between A and B? Well, the path difference, again, same as the previous problem, is going to be half lambda. They are successive points where we go from constructive to destructive interference. They must have the same n. Who cares what the n is, all right? Because if you do the math, delta L at A and delta L at B, all right? Both of these are the conditions for constructive and destructive interference, respectively. You take the difference of both of those, and we get half lambda. I'm ignoring the negative sign here, or maybe it's better if I just do delta L B sub B minus delta L sub A, and we'll get the answer that way. So anyways, point is though, is that again, all right, the path difference between both is half lambda. Well, what's the path difference in terms of how far the waves have to travel? Same as before, it's 2 times that little line segment in there. One wave has to travel that line segment more, and the other wave travels that line segment less to get to that point from the previous point. And so what we see is that line segment AB is equal to 1/4 of the wavelength, and therefore that car has traveled 0.83 meters, okay? Which is, I believe, the question asks us to find the minimum distance AB, all right? That's the minimum distance because it's successive constructive to destructive interference. We get bigger distances if we, assume that we go from constructive to destructive, back to destructive, going to separate different ends. All right? Okay, that's some good practice right there. Hope you got that. If not, email me questions. And the next video is gonna talk about diffraction.